Greetings, A-Life 2021. My name is Derek Whitley. I'm a dual PhD candidate in complex systems and cognitive science at Indiana University, and today I'll be talking to you about my work resurrecting FPGA intrinsic analog evolvable hardware. Throughout the course of this talk, I'll provide a bit of background and motivation before moving into the novel methodology created for this work. Then I'll present the approach and results for each experiment, talk briefly about the open sourcing of this project and our dedication to community outreach for continued work before wrapping up. So let's get started. What is evolvable hardware? Simply put, evolvable hardware is the application of evolutionary algorithms to hardware systems either during design, operation, or both. Historically speaking, evolvable hardware was born around the same time as evolutionary robotics, and I'd be remiss not to tip my hat at the University of Sussex for birthing both approaches in the same few years. They are differentiated by their specific focuses. Evolutionary robotics targets the coupling of the sensory, cognitive, and effectory systems, whereas evolvable hardware is particularly focused on the physical system itself. At first, evolvable hardware only targeted the physical construction of cognitive or processing systems, but as the field matured, it spread its focus across other mechanical, electronic, architectural, and radio systems. But to constrain the scope for this project, we'll only be discussing evolvable hardware in the context of the processing system. Now, for a very brief history lesson, you may remember the hype of evolvable hardware just before the turn of the century when Adrian Thompson at the University of Sussex succeeded in evolving an analog circuit that could discriminate between a 1 kilohertz and a 10 kilohertz tone. This was remarkable for several reasons. Firstly, the circuit was evolved in the absence of a clock, suggesting that evolution independently generated complex internal circuit dynamics for determining frequency. Secondly, that the number of configurable logic blocks, or CLBs, used on his Xilinx XC6216 field programmable gate array was a parsimonious 42 out of the available 100. And lastly, perhaps most magical of all, the circuit that evolution created employed untraceable physical phenomena that was not directly accessible on the genotype-phenotype map. To this day, the hidden characteristics utilized by the circuit are not fully understood. This experiment was profound in that it demonstrated the search power of evolution, not just by generating a parsimonious analog circuit, but also by incorporating hidden environmental elements into its fitness. However, not more than a decade after this famous experiment, research into FPGA intrinsic analog evolvable hardware seemed to dry up. Let's take a look at the timeline. In 1991, while working on embryological electronics, Australian computer scientist Hugo de Garis postulated that evolutionary algorithms such as genetic programming will probably lead to electronic circuits being grown in special hardware. Just a few years later, Adrian Thompson crystallized this approach with his tone discriminator experiment, as previously discussed. Then in 1999, the Xilinx Corporation discontinued the XC6200 series FPGA. This singular event was responsible for the dissipation in early evolvable hardware research. To comprehend the impact of this loss, you must understand that the XC6200 series was the only FPGA with a fully documented bit stream available to the end user. Without this documentation, evolvable hardware practitioners were unable to map the hardware resources available on an FPGA to a genotype. Xilinx moved to encrypted and undocumented bit streams for economical and security reasons. There's virtually no profit incentive to maintaining an open bit stream, and having it open is a security risk for the reverse engineering of intellectual property. Fortunately for evolvable hardware, the hacker community desperately wants an open bit stream for developing inexpensive and open source FPGA development tools. In 2015, at the Chaos Communication Congress in Hamburg, Germany, Project IceStorm announced the full reverse engineering of the Lattice Ice40 bitstream. Ultimately, yet unintentionally, this made FPGA intrinsic analog evolvable hardware possible once again. Now that we have some motivation and knowledge of the relevant history, let's take a look at the goals for this project. First, we want to recreate the method of bitstream evolution for this type of evolvable hardware. Then we want to demonstrate that the method works at all. Once we have established proof of concept, try to recreate key experiments that generated excitement in analog evolvable hardware, and then finally, forge a solution that allows others to share in the excitement of FPGA intrinsic analog evolvable hardware. All of the code, tools, schematics, setups, and troubleshooting techniques have been made available at evolvablehardware.org and GitHub. If you have an interest in this field, please reach out. Our hope is that this work inspires a new generation of evolvable hardware researchers. With these goals in mind, let's get started. Starting with the fundamentals, we'll cover FPGAs, bit streams, and circuit evolution. FPGAs, or Field Programmable Gate Arrays, are a type of universal computing tool constructed of a matrix of addressable logic elements in reconfigurable interconnects. Unlike a conventional computer processor that takes procedural instructions in binary form, an FPGA accepts a stream of binary bits known as the bit stream to construct a circuit. The bit stream of an FPGA is the binary representation of the circuit to be encoded using the available resources on the FPGA. Bitstream formats vary by manufacturer, make, and model, meaning the bitstream for a given circuit will not be interpretable by a different model of FPGA. For the work performed here, we will focus specifically on the Lattice ICE40 HX1K FPGA and the bitstream format reverse engineered by Project IceStorm. Next, we will discuss the specific methodology that makes this work possible, the experimental setup, the technical design, and the necessary constraints. But before getting started there, it's an important technological difference to note between FPGAs used in past evolvable hardware experiments and those available today. Modern FPGAs have made over 2 decades worth of advancements and contain highly sophisticated signal routing mechanisms and very dense logic capabilities. To avoid creating an overly complicated routing interpreter, while still attempting to mimic the routing and logic used in Thomson's experiments as closely as possible, we implemented local routing in the form of Moore's neighborhood. A further consideration is the sheer combinatorial complexity of a raw bit stream. If unconstrained, the HX1K can generate 2 to the power of 138,240 unique bit streams, a search space far too large for any existing algorithm. So to engage both of these considerations, we must take a close look at our FPGA's internal design to determine how we can constrain evolution. Looking at an X-ray snapshot, we see that, like most FPGAs, the HX1K is constructed of a matrix of configurable logic blocks. Most are specialized for logic operations, while others for input, output, and more still for random access memory. Given that Thomson constrained his FPGA to 100 CLBs, we constrain ours as close to that number as possible by activating only the central column, which contains 96. We're unable to match the exact number without performing more exotic routing, as the columns left and right of the central column are specialized RAM tiles. Every CLB contains a partial bit stream with a standardized format. Going one step deeper, we examine this bit stream map for just one of our active CLBs and notice that there's quite a bit of horizontal symmetry. And without going into painful detail of what each bit does, we can see that there are red bits for routing, green bits for internal block configuration, and blue bits for logic function. Recalling that the total bit stream combinatorial complexity is insurmountable and that we only need each block to have basic local routing and logic, we can begin applying our constraints. That's much easier to look at. By locking these rows and columns, we now have access to basic routing, input configuration, and logic function, all for the price of 20 bits per configurable logic block, which is as close as we can get to Thomson's setup, which utilized 18 bits per block. To clarify, these 20 bits represent the ordered set for just one of the 96 CLBs for our genotype. When combined with the other 95 CLBs, the total genotypic length is 1,920 bits. Finally, let's take a look at our experimental setup. A host computer running an evolutionary algorithm will generate a population of candidate bit streams that are systematically uploaded to the FPGA to run for a period of time. Meanwhile, a microcontroller takes input from the FPGA's designated output pin and performs analog to digital conversion on the analog output signal. After capturing the waveform, the microcontroller transmits the ordered set of waveform samples over serial interface back to the evolutionary algorithm running on the host computer, where fitness is then calculated. An additional connection between the microcontroller and FPGA is in place for later experiments. A final consideration that must be addressed is the upload time for transmitting a single bit stream to an FPGA, which on average takes about 3.5 seconds. And considering that a single evolutionary experiment may evaluate tens or even hundreds of thousands of circuits, the wall clock time for completion extends from hours to days to weeks, something to keep in mind when thinking about trying different parameters in a given experiment. We're now ready to test proof of concept operation. Doing so, we wanted to take the simplest approach to analog circuit evolution as possible. This first meant evaluating the components of the signal we would be receiving to determine what we wanted to manipulate. Knowing that the signal produced from the FPGA is a continuous wave and that the microcontroller can only capture a sampled portion of it, our options for waveform manipulation are limited to the microcontroller's sampling capacity. Knowing that the continuous signal emitted from the FPGA is sampled at a set frequency and stored as an ordered list of values, we're able to reconstruct a digital replica of the waveform. And by taking the absolute difference of each sequentially sampled pair, we are able to determine whether a signal is changing and by what quantity. Further, by summing these differentials, we are able to determine which circuit from a given population has the maximum change in its output signal. So this is what we'll evolve for, circuits that produce larger amplitude signals than their previous generation. So for our first experiment, we set the following parameters for a standard genetic algorithm: a population of 50 circuits to evolve over a course of 100 generations through tournament selection. The probability for a given gene to mutate was 1 in 10,000, with the probability of crossover at 70%. The top 10% of each generation was considered elite and not mutated. The fitness function, termed amplitude maximization, also variance maximization, equals the sum of all absolute differentials over the number of samples in the ordered set. Recalling that the upload time per circuit is about 3.5 seconds and that we are going to be evaluating 5,000 circuits, the estimated wall time for completion is just under 5 hours for this very short experiment. As you can see, the best fitness per generation, as indicated by the blue line, gradually increased for 40 generations before stagnating for nearly 30, then catapulting to twice, then 3 times the fitness before the algorithm terminated at 100 generations. The population's mean fitness, the green line, trailed comfortably behind the best fitness throughout the entire experiment, achieving about 70% of the max fitness with about a 10-generation delay. Now let's take a look at the output signal as measured by the microcontroller. What you're seeing is a looped GIF of each generation's best circuit output. Similar to the previous plot, you may notice that the signal's amplitude grows slowly for the first 40 generations, then remains somewhat stagnant until jumping largely in the last 20 generations. Interesting to note, the signal of the first 10 generations has expectedly low amplitude, but hovers near the maximum output voltage. Subsequently, it appears that evolution found better fitness at lower voltages for this particular experiment. So let's recap. We were able to show proof of concept operation for an FPGA intrinsic analog evolvable hardware technique that evolved circuits directly on the FPGA without the use of a clock. Next, we will attempt to reproduce one of Thomson's experiments, the evolution of a millisecond oscillator. This next goal is one of evolvable hardware's seminal experiments, which we considered to be the next simplest in the lineup, Adrian Thompson's Kilohertz Oscillator circuit. Oscillators come in many shapes and sizes, especially when it comes to electronically generated waveforms. There are sine waves, square waves, sawtooth, triangle, and pulse waves. But in order to remain agnostic of the waveform, there are a few target attributes shared by each that we are concerned with. We set a target frequency of 1 kilohertz, fix the amplitude to the microcontroller's trigger voltage, which is about 2.25 volts, and lock the sampling period to 1 second. Doing so will allow us to measure the frequency of an output signal using the microcontroller's built-in interrupt handler. Let's take a look at how that works. No matter the oscillator's form, should the signal emitted from the FPGA cross the MCU's reference voltage, an interrupt event will be triggered. If the interrupt event is a rising edge, meaning the voltage started low then went high, we start an internal timer for 1 second, add an integer of 1 to our pulse counter in the microcontroller's memory buffer, then wait for and count subsequent rising edges. This is how the microcontroller is able to capture the FPGA's output signal frequency. When the 1 second period is lapsed, the microcontroller transmits the number of rising edges back to the host CPU, relaxes the interrupt handler, and waits for further commands. Now that we've established the mechanisms, let's look at our parameters. Similar to the previous experiment, we generate a population of 50 candidate circuits, evolve them for 100 generations via tournament selection with a mutation probability of 0.001, crossover of 0.7, and an elitism fraction of 0.1. This fitness function, copied from Thomson's work, is much simpler than the previous experiment in that it takes the inverse of the absolute difference of the target frequency and measured frequency. This means fitness will climb as the measured frequency approaches the target frequency. Lastly, and not pictured here, a special condition is implemented when the measured frequency perfectly matches the target frequency. This occurs to bypass a divide by zero and results in a fitness of 1,000 assigned to that candidate circuit. As illustrated in this plot, the best circuit fitness per generation, again in blue, gradually increases in fitness for about 75 generations before launching to maximum fitness. Interestingly, each generation's mean fitness, again in green, appeared to hover near zero. Let's take a look at the fitness as a function of pulses counted in log form. This box plot looks more like what we might expect. The population's mean fitness, while a bit unsteady, does in fact grow. This suggests a couple of considerations we intend to explore in future work. Firstly, fitness assignments for this function are nonlinearly related to the signal measured. For example, a circuit that generates 997 pulses has a fitness of 0.33, where a circuit that generates 998 pulses has a fitness of 0.5. Linearizing fitness assignment could massage the population's mean fitness to something more stable. Secondly, the unsteadiness of mean fitness growth may be a result of using rising edge interrupt handlers to count pulses, an evaluation mechanism which may be too coarse for the creation of stable analog oscillators, a sentiment echoed in Thomson's work. Let's go ahead and take a look at the output signal. Instead of a clean wave with any kind of stable periodicity, this plot illustrates the best circuit generated by evolution outputting a near maximum voltage that sporadically drops below the microcontroller's trigger voltage, only to rise back up to near max voltage. Though it is technically a solution to the constraints applied to evolution, the circuit behaves much more differently than we might have expected it to. Further, the period between pulses exhibits little or no discernible pattern, yet somehow the circuit produces roughly 1,000 pulses per second. We decided to test environmental effects by heating and cooling the FPGA, as well as uploading the evolved circuit to 3 different FPGAs of similar make and model. Heat caused a dramatic increase in frequency before halting at some upper limit, and cooling delayed all circuit output for several minutes until the FPGA achieved its standard operating temperature. And when uploaded to different FPGAs, 2 of the 3 failed to output a signal at all, while the third output a signal of completely different frequency. Now let's recap this project stage. Our goal was to reproduce one of analog evolvable hardware's experimental results, the production of a millisecond oscillator, which we did. However, after analyzing results and observing circuit behavior, further questions were generated. We drew inferences concerning the types and behaviors of oscillators, many of which, according to the literature, had yet to be generated on an FPGA. So an open question is, are other waveforms evolvable? We made observations about the periodic stability of oscillators produced by evolution. Is periodic stability evolvable, and if so, how stable? And finally, it could be that frequency production is significantly impacted by the fabrication resolution of the FPGA. Can higher or lower frequencies be generated, and what is the limit? These are questions to consider for future research. For the last experiment, we aim to reproduce Adrian Thompson's tone discriminator results. As mentioned previously, the goal is to evolve a circuit that can classify a 1 kHz tone from a 10 kHz tone. Please note that from this point in the presentation, everything is a work in progress. Before inputting tones into the FPGA for classification, we need to adjust our device setup. The microcontroller used in our setup is capable of outputting square wave tones at its primary operating voltage of 5 volts. However, the FPGA has an operating voltage of 3.3 volts. Inputting a 5-volt tone into a 3.3-volt FPGA will permanently damage the I/O and logic fabric of the FPGA. To overcome this, a logic level converter was added to the experimental setup to appropriately step down the input signal to the FPGA while still maintaining tonal integrity. Additionally, an integrating operational amplifier was added to the setup to magnify the output signal of the FPGA while simultaneously integrating the output voltage for simple ADC readout by the microcontroller. Simply put, this device acts as a binary memory buffer for the microcontroller, as the latter does not have enough memory to store hundreds of thousands of microseconds worth of waveform data. The integrating op-amp is then situated between the FPGA and the microcontroller, and with that, we are now ready to start our experiment. We set the population to 50, generations to 5,000, and the rest of the parameters same as before. Utilizing Thomson's tone discriminator function, fitness is measured by exposing the FPGA to one of two tones, 10 kHz or 1 kHz. Each tone is emitted 5 times in random order for a duration of 500 milliseconds, resulting in an evaluation period of 5 seconds. The output from the FPGA in the presence of a tone is integrated into the op-amp, which is then read as either a 1 or a 0 by the microcontroller before being reset in preparation of the next tone. Fitness is determined by summing each set of sampled frequencies independently, then taking the absolute difference of the two sets. The maximization of this difference yields a better discriminator. A very important note is that the necessary time to upload and evaluate a circuit using this fitness function results in no less than 8.5 seconds per circuit. And by evaluating 250,000 circuits, the total experiment duration is approximately 24 days. Disappointingly, evolution appears to have gotten stuck in a local optima, ending the nearly 20-day endeavor with a best fitness of 62%. However, after many more trials and lots of messing around with parameters and evaluation periods, we were able to intrinsically evolve a circuit with suboptimal discrimination characteristics using a simulated operational amplifier as opposed to the physical op-amp. We posit that using a simulated op-amp relieves part of the setup from extraneous environmental noise, including signal crosstalk and temperature variations. The top plot shows the output voltage from the simulated op-amp and is vertically aligned with the bottom plot, which shows the order of tonal input. You can see that the evolved circuit more effectively classifies the 1 kHz over the 10 kHz tone. Although this work is still ongoing, we feel that up to this point we have sufficiently generated the necessary positive results to inspire further research while validating the previous generation of results. And with that, we're confident in saying that FPGA intrinsic analog evolvable hardware is resurrected. For the longest time, evolvable hardware has been nearly inaccessible to those who would be interested. There was a lot of excitement, but also a lot of mystery about using evolution to design circuits, not to mention the number of barriers to entry. Our hope is that this work inspires further research. So to facilitate that, we have open sourced the entire project and are organizing to help fill the research gaps that remain. We have published our code, materials, setup, tutorials, and troubleshooting techniques at evolvablehardware.org and GitHub. Compared to the industry-grade components used in past experiments, costing thousands of dollars, the work performed here was intentionally performed with inexpensive, off-the-shelf parts totaling $85. You can find the bill of materials, setup instructions, and more project ideas at evolvablehardware.org. We have an active Slack workspace where we organize, develop, and debug new and existing projects in conjunction with the Evolvable Hardware GitHub organization. Please reach out to us if you have any interest in collaborating or getting set up. Now let's wrap it all up. From the onset, our goals were to modernize analog evolvable hardware by creating a bitstream evolution technique using modern field programmable gate arrays, prove the method's concept of operation, reproduce at least one of the field's seminal experiments, and provide a toolkit that empowers other researchers to get involved. And though there's still much work to do, we believe we have accomplished those goals. Now onward to future work, we are designing experiments to evolve fully analog sine wave generators, and in related work, the creation of periodically stable oscillators. We are also very excited at the prospect of employing this method toward electronic reservoir computing techniques, and also towards speech recognition and synthesis circuits. Finally, we would like to extend a very, very special thanks to Professor Randy Beer and Professor Eduardo Izquierdo for their support and insight into this project. This work was performed by me, Derek Whitley, Professor Jason Yoder at the Rose-Hulman Institute of Technology, and hardware wizard Nicklas Carpenter. Please contact us with any questions or concerns.